Let's talk a little bit more about the square function that gave us the sinc function Fourier transform. We're going to look at it again, but this time we're going to look at it in a little bit more of a generic fashion. So let's draw a generic square pulse centered around t equals 0. And instead of specifying a width in terms of specific numbers of seconds, let's specify the widths in terms of a parameter. Let's call it, it goes from t equals minus a seconds to t equals plus a seconds. And let's say that it has an area, let's use a different color. Let's say that it has an area of a, capital A, we'll call it just area. How about that? We won't even abbreviate it. Okay, so let's say it has a total of area, which means that its height has to be area over 2a. Okay, so if the area is 2a, so if the height is 2a, let's try that one more time. If the height is area over 2a, height times width gives me an area of area. And the reason I'm going to do this is I'm going to solve for the Fourier transform of a generic square wave, and in doing so I won't have to keep resolving it every time I see a different square pulse like this, and we're going to see a lot of different square pulses, so it's nice to just do it once and then never have to do it again. So let's solve for a of omega. So a of omega is going to equal the integral from minus a to a of x of t, which is area over 2a, times e to the minus j omega t dt. So the area over 2a comes out, that's a constant. We get a 1 over minus j omega from the integral, and then we're left with e to the minus j omega a minus e to the plus j omega a. And by now we should be getting good at recognizing that this term here is minus 2j sine a omega. So putting it all together, we wind up with, let's see what cancels actually. We know the j cancels the j, the minus cancels the minus, the 2 cancels the 2. That's awfully convenient. And what we're left with is sine of a omega over a omega times area. Okay, and we'll put a box around that because that looks like we're pretty much done. And just as a reminder, because this function that we're working on, because this square pulse is an even function, the Fourier transform turned out to be purely real. Okay, there's no imaginary part. That's just a special case. Okay, and then finally we're going to have a quick idea. We're just going to plot the magnitude response of this. So we'll hold off on the phase response for now. So this is the magnitude of a of omega. And it's going to work as such. The sinc function always has a shape that looks like this. And so what you can imagine is that it's sort of a sine function where the amplitude of the sine function is inversely proportional to omega. So you can see that as omega gets bigger, the sine amplitude gets smaller. If it was just sine a omega over a omega, then you could use L'Hopital's rule to determine that at omega equals 0, the amplitude is 1. In this case, it's an amplitude of 1 scaled by the area. So whatever the area was before, this is now equal to, that's that height. So where I got that from was just a reminder, sine of a omega over a omega evaluated at omega equals 0. Well, that gives you 0 over 0. So you use L'Hopital's rule. I believe that O has an accent sign on it. And when you do that, that gives you, let's see if I can do this, that should give you a cosine of a omega. That's the derivative of the numerator. divided by the derivative of the denominator, again evaluated at omega equals 0, and that's going to give you 1. Okay, and then in our case it's 1 times the area. Good. So that's the generic shape of the sinc function. The last thing that we need to work out is exactly at what frequencies these zero crossings occur. Okay, and to figure that out, we know that the sinc function has to equal 0 when the numerator equals 0. That's just how all these functions work. So in other words, let's work out where sine of a omega equals 0. Because if I know where sine of a omega equals 0, I'll know where the sinc function equals 0. Well, what values of a omega are going to make the sine function equal to 0? Well, we know that the way sine functions work, sine of pi equals 0, sine of 2 pi equals 0, 3 pi equals 0, and in general, integer multiples of pi, sine of integer multiples of pi give us 0. So therefore, we can say that if a omega equals an integer multiple of pi, then we have a 0 crossing. And that occurs at frequency of omega equals pi over a times n. So this is pi over a, 2 pi over a, 3 pi over a, and so on. Now, here's where this starts to get really interesting. Let's compare the Fourier transform of two different square pulses. Let's say that we have one that looks like this and another that looks like this. And so you can see that one is taller but skinnier than the other. And the reason I've made one skinnier and taller, we're going to say that the areas are the same. So the areas are the same, but what's different is the value of A. So we know that we can tell that the red A is smaller than the blue A. Okay? So what does that mean in terms of the Fourier transform? Well, it means a couple interesting things. We know that if A gets smaller, the zero crossings 1 over A get bigger. So in other words, if we were to look at the corresponding magnitude responses, we would tell that, let's say the blue signal had a Fourier transform that looked like this. Let's say it was a sinc function that looked as such. The red signal, because it has a smaller value of A, that means its zero crossings, which are 1 over A, are going to be larger. Okay, I don't know exactly how large because I didn't put actual numbers here. Okay, but you get the idea. So in other words, as your pulse, as your square pulse gets skinnier with respect to time, it gets wider with respect to frequency, which sort of makes sense. If your signal gets skinnier with respect to time, that means it contains higher and higher frequencies. Okay, if you look at the red signal, you need higher and higher frequency cosines in order to match this very small pulse. You need higher frequency cosines to build that than you did with the blue pulse. Okay, and if you need higher frequency cosines, it stands to reason that the Fourier transform should be more spread out with respect to frequency so that you get more higher frequencies. Okay, so a final parting thought: what happens if you let A go to infinity? Okay, if you let A go to infinity, that means you're making a pulse that is infinitely wide. Infinitely wide with respect to time. And that, of course, if you make a pulse that's infinitely wide with respect to time, that's how you get a constant function. Okay, that's just an infinitely wide pulse is just another way of thinking about a constant. Well, according to what we're looking at, as a gets bigger and bigger and bigger, 1 over a gets smaller and smaller and smaller, and therefore that sinc function, that infinitely skinny sinc function, should be magnitude of a of omega. That infinitely skinny sinc function should just be kind of like an infinitely skinny box right here at omega equals 0. And that's what we call the impulse. That is an impulse function. That's delta of omega. And what's interesting is it tells us what we already knew, which is that a constant function contains energy only at omega equals 0. Now if we go the other direction, if we let our time pulse get infinitely skinny, if we let it get infinitely skinny with respect to time, then it starts to look like, as it gets skinnier and taller and skinnier and taller, and the limit that a goes to 0, it winds up being so infinitely skinny and so infinitely tall that what you wind up with is x of t is an impulse with respect to time. Okay? An impulse is infinitely skinny and infinitely tall. Well, what happens in the frequency domain? According to our theory, as the time pulse gets skinnier and skinnier and skinnier, the frequency pulse gets broader and broader and broader. Okay? In fact, that sinc pulse gets so wide that it becomes infinitely wide, and it becomes, you're not going to believe it, it becomes a constant with respect to frequency, which is kind of nutty. So what that tells us is that time impulses contain all frequencies in equal measure. Okay? This is a very useful property of time impulses. They have all frequencies in equal measure. And so because it has that property, we're going to wind up using delta functions a lot, time impulses a lot. But for now, let's just try to remember the fact that the Fourier transform of a square pulse, such as the one we're looking at here, always yields a sinc function with respect to magnitude.